Welcome to the Statics and Strength of Materials, Lecture 7. Today we'll be discussing moments and equivalent systems. The outline of this presentation is moment of a force about a point will be discussed, moment of a force about an axis, moment due to a couple, and system of forces and moments. I'll be discussing the definition of moment. What is moment? Moment of a force is a measure of its tendency to cause a body to rotate about a specific point or axis. As an example, here I have a force F, which is at a distance d from point P. And if I were applied this force F at a distance d from point P, this force will cause a moment about P. For example, say I have a wrench, and that wrench was applying a force to a bolt at point P. This wrench, when a force is applied, will cause a rotation of this wrench. It will cause a moment about P. Note that this force F was closer to the bolt. It will be much harder to rotate that bolt versus if that force was farther away, because that will cause greater moment. As an example, this force F, the farther away is from point P, that force will cause greater moment than a force that's much closer to point P. In fact, if this force F passes through the line of action of point P, no moment will be applied. You can see that here in the wrench. If a force F was applied, if you were to apply a force right at where the bolt is, there will be no moment. Nothing will happen. Here, you can also see that the direction of the moment is counterclockwise. In the second example, we also see the situation of a wrench, about an axis in this case. In this case, the wrench is applied about an axis, but it will also cause a moment about this axis along this tube. Here's another example of moments are acting about an axis. Here you have person B who has a weight of 500 newtons and is 2 meters away from this axis. Here you have a person A, which is 1,000 newton, has a weight of 1,000 newton, is 1 meter away from this axis. Each of these persons are exerting an amount of moment about this axis. Moment equals force times distance. D is the perpendicular distance of that point O to the line of action of force F. For example, if I have a point O and I have a force F, the moment, the magnitude of that moment is going to be that distance D1 times the force F1, as an example. If that force was passing through point O, that will cause no moment because the line of action of that force is passing through point O. If you have several forces, F1, F2, F3, each of them will produce also a moment, and you can basically superimpose their effects. So for example, what is the total moment due to these three forces applied at a distance O? It will be F1 times D1 plus F2 times D2 plus F3 times D3. The direction is perpendicular to D and F in this case. So the direction of that moment will be perpendicular to both D, this distance here, and the direction of the force. Say as an example, I apply a television near the wall. That will minimize the moment exerted on the support of the shelf at point P. If I put the same television away, farther away, then that will cause greater moment at point P, and it will be easier to break the support. Here's an example of a crane. This crane uses a counterbalance weight to be able to pick up this object. And this counterbalance, the weight that's required to counterbalance this weight can be determined. If we take moments about P, we want to make sure that this weight W1 times D1 is equal to W2 times D2. how to calculate moment of a force about a point. So in summary, what I can do, I can take this force times this distance to calculate the total moment um, due to this force at a distance d from point O. Notice that this moment here is acting um, perpendicular to this distance here, and this force has to be perpendicular to both of this. And moment is a vector quantity. So far, I only considered moment as a magnitude, but in reality, it has a direction, and it tells us in which direction the moment is getting applied. If the force tends to rotate the structure clockwise, the sense of this moment vector is out of plane of the structure, and we consider the magnitude of the moment as positive. If the force is applied in the opposite direction, then the moment will be acting in the opposite direction, and we will consider this moment to be counterclockwise direction. We will consider this moment to be negative. Let's go through some examples to demonstrate and illustrate how to determine the magnitude of the moment um, for this particular problem. Say you have this device, which is attached to the wall. The question is, what is the moment of the 40 kilonewton force about point A? So very simply, what you can do, there's few approaches to this problem. You can draw a dashed line all the way back, so as such, these 30 degrees. We know this distance is 6 meters, and the force applied is 40 kilonewtons. So then the moment applied will be 40 kilonewtons times this distance. Since I know there is 6 meters and this 30 degrees, this angle here is also 30 degrees. And so therefore it's very simple to then determine this distance d. This distance d is 6 meters times the sine of 30 degrees. And that'll give me 3 meters. As a consequence, now all I have to do is to determine this force. So basically this distance times this force gives me the moment about A. And that's 3 meters times 40 kilonewtons. That gives me 120 kilonewtons per times meter. Notice that the unit is force times length. And also notice the direction of the moment is counterclockwise. Also, one thing I want to point out in this example is that I can solve this problem in a different way. Say I take this force and I decomposed it into the y-axis and x-axis. This force of 40 kilonewtons times cosine of 30 degrees will be the force in the x-axis and pointed to the right. However, that force will cause zero moment about point A because it goes through a line of action of point A. However, 40 kilonewtons times the sine of 30 degrees gives me the vertical um, force component, and that 40 kilonewtons times sine of 30 degrees times 6 meters gives me the moment about A, actually. So you can see here quickly that this 40 kilonewtons decomposed into the y-axis force gives me a 40 kilonewtons times sine of 30 degrees, which is 20 kilonewtons, times this distance of 6 meters gives me 120 kilonewtons times a meter. You can see there that I was able to get the same answer with two different approaches. Moment of a system of forces. Say I have 4 different forces acting on the machine part, this part right here. The question is, what is the sum of the moments of the forces about this origin O? Very quickly, you notice that this 3 kilonewton force passes through the point at which moment wants to be calculated at. So therefore, this 3 kilonewton force causes no moment about point O. The 5 kilonewton force also causes zero moment about O because it passes through the line of action where moment will be calculated at. The 2 kilonewton force is pointed downwards, and you can see here that distance is 300 millimeters away from point O. And so that moment caused by this force going downwards is 2 kilonewtons times 300 millimeters. You also have a moment caused by this 4 kilonewton, which is at a 30-degree angle relative to the x-axis. What I can do about that one, I can decompose the 4 kilonewton into the x component and the y component. The 4 kilonewton times cosine of 30 degrees gives me the x component, while 4 kilonewton times sine of 30 degrees gives me the y component. The good news is that that force times this distance is known. It's about 700 millimeters, while the x component to the distance O, the distance to point O, perpendicular distance to point O, is known and is 300 millimeters. So we can quickly calculate the moment contribution due to each of these forces. So here you see that the moment for the 2 kilonewton, the moment for 2 kilonewton times the distance, 300 millimeters, can be calculated. We change the unit to meters to make it consistent. And so we get 0.3 meters times 2 kilonewtons is minus 0.6 kilonewtons times meter. And note that the direction is clockwise for this force. It's acting in the negative direction. Now I'm ready to decompose this force into two components, x-axis and y-axis. The x-axis gives me 4 cosine 30 degrees times the distance of 300 millimeters from point O, that distance, perpendicular distance, gives me a quantity of minus 1.039 kilonewton times meter. And so that force is also in the clockwise direction and is negative. You can see that. The perpendicular distance from point O to the line of action of the y component, so this component right here, that distance is 700 millimeters. So I can do that multiplication and I get 1.4 kilonewton times meter. So now I have to take these three moments I calculated and add them up. So summation of the moments gives you minus 0.239 kilonewtons times meter. And so that's a clockwise moment about 0.0. And this gives me the tendency of these forces to cause the body to rotate. Example 3 is yet another example of a very similar problem. Here I have a weight for this linkage of 300 pounds. The sum of the moments about C due to this weight and the force exerted at the bar CA by the cable AB is 0. The question is, what is the tension in the cable? So what is the tension in the cable, in this cable here? The first step is to determine there's a tension force acting on this cable. So I can cut it right there to figure out what that is. So I know the slope of this cable. So I can calculate that this y component is 3/5 times tension force T. That this component right here is 4/5 tension T. So I was able to decompose these tension forces. And I also have this weight right here. So the question is the sum of the moments about C due to the weight and the force exerted on the bar CA by the cable AB is 0. So what I have, that moment has to be 0 according to the problem statement. And so then I can take the 4/5 tension force in the x direction and multiply by this distance to point C, and that will give me the first component of the moment that we want to calculate. And then I have the 3/5 times tension load of this cable in the y direction times the distance from this point to C. And that distance is actually 4 feet. So all I have to do is multiply that to get the moment about C. And then finally I have the weight W, which is at a distance of 2 feet. That's minus twice W. I can add all that up and that's equal to 0. Then, because this problem statement says that the moment, the sum of moments about C is 0 due to all these forces. Therefore, I can now solve for T, and T gives me 0.357 times weight. I know the weight is 300 pounds, so therefore the tension on the cable must be 107.1 for the moment to be 0 about C. So that's a good problem because it shows how the moments, some moments about a point can be used to determine an unknown force. Example 4 is very simple. Now that you have the expertise and experience, we can tackle it very quickly. We want to calculate the moment about O, and we can do that for a given force of 100 pounds going downwards. What we could do in this problem, we can decompose the 100 pounds in a perpendicular to the AO line, and then so it's also along the AO line. So we can take this force and decompose into two components. That's one way of doing it. And I think you can simply do that. For example, this 100 pound, right, can be projected into this axis. So how do we determine that? If this is 60 degrees, then this is 30 degrees. So 100 times the cosine of 30 degrees gives me the force component along this axis. However, that force component passes through the line of action of point O, so that causes no moment. However, if I take this force and calculate the force component perpendicular to AO, then that component will be the 100 times cosine of 60 degrees. And so that will give me 50 pounds. And so I have to multiply 50 pounds times 24 inches. And that will give me a total of 1,200 pounds times inch. So that's the approach to solving this problem. That's one approach. Another approach is to figure out if I have this force, what is the distance of this force to point O? I know the distance here, D. If this is 24 and this is 60 degrees, then this distance is simply 12 inches, or 24 inches times the cosine of 60, that's 12 inches. So I know this distance, I know this 100, so 100 times 12 is 1,200 pounds, 2 times inch. Two different ways of doing the problem. Example 5 is yet another example where you have, say, a flagpole. This flagpole is supported by a tension in T from this cable to the ground. And we know it needs to supply a moment about O of 72 kilonewtons times meter. The question is, what tension T will do that for us? Well, the first step is to draw a diagram, simple diagram here, showing all the angles, this 30 meters. So basically showing the relative information. The information is relevant to the problem. And these 12 meters as an example. And so what we want to do is calculate the distance between O and this perpendicular line. And if we can do that, we can determine what value T will make that happen. So there's many different approaches to approach this problem, actually. So that distance can be calculated very quickly. I won't go through the trigonometry in great care because I think you can figure out how to do that. But in general, you want to find this distance here. You want to find this angle here. And once you have this angle, and since you know there's 12 meters, you can determine this distance. And so all you have to do is then, you know the tension, you don't know the tension, but you know the tension times the distance has to be equal to 72. And so very quickly, we can determine the tension on the cable to be 8.65 to make that happen, kilonewtons. So what about a more generic problem? What about a more complex problem where it's not clear that you can do it? You can do this calculation in a simple way. Moment is a vector. Moment can be represented by a vector. And if you recall, a force vector is defined by its magnitude and direction. In this case, this force is oriented in some direction, has a magnitude. And its effect on the rigid body also depends on its point of application. The moment of this force F about point O, like what is the moment that causes that moment at point O, can be calculated simply by drawing a position vector that goes from point O to the line of action where force F is applied. So R cross F, the cross product of R and F, will give us the moment, that torque. The moment direction will be perpendicular to both R and F. This will be the more automated way of doing the problem. All you have to do is calculate the position vector of R, which goes from the point where the moment is calculated to the location where the force is applied. And then you calculate the direction of the force and make sure you have it clearly defined, the force vector. And then R cross F will give you that moment. So the magnitude of the moment M measures the tendency of the force to cause a rotation of the body, as we had explained earlier. And it will be equal to M equals R times F. So the magnitude of R, the magnitude of F times sine of theta, where theta is the angle between R and F. That's the definition of the cross product. But note that note that R sine theta is basically this distance d. So the perpendicular distance of force F to this to point O, that distance there is d. So that's another way to calculate as F times d. The sense of the moment may be determined by the right-hand rule. Put your index finger along this axis, your four fingers along this axis, and then rotate it to close on F. And so you're coming from here with your four fingers, and then you rotate your hands to go to F. And that shows you, with a thumb, you can determine which way the moment should go. Here is going upwards. We know that from using that technique. I also want you to note something. For example, here I drew a position vector R to where the point F is applied. And that's a way to calculate the moment is R cross F. That's what we explained. And here's another diagram showing the same thing. That if I take the force F, the magnitude times d, this distance, that'll give you the moment, the magnitude. But I can also determine that by taking the magnitude of R, magnitude of F, and multiplying by the sine of alpha, this angle here between R and F, and that will also give me the magnitude of the moment. Notice that the unit of the moment is force times length. What happens if I take a position vector R, but that goes from A to Y or from A to Z? It turns out that if I take the cross product of this position vector AZ against F, that cross product will give me the same answer as the moment calculated by taking a position vector R from A to X, where the force is applied. The same happens if I take a moment calculation such that the position vector goes from A to Y, and I took the cross product of that position vector from A to Y, cross product to F, you will find that they're all equal and the same. So in essence, it doesn't matter how you calculate that position vector, as long as that position vector ends at the line of action force F, then if you take the cross product of that position vector with F, you will get the moment calculation correctly. I want to point out, and I think it should be obvious, that if I have several forces, and we kind of did it earlier, but we can repeat it now, is that if I calculate the moment about, due to forces F1, F2, F3, F4, All I have to do is to find the position vector from O to A, and then from there calculate R cross F1, R cross F2, R cross F3, R cross F4, and add them all up to get the moment effect about O due to these forces being applied at point A. Note clearly that since all these forces are concurrent to A, I can determine a resultant force at A and its angle, and then basically calculate R cross times the resultant F and determine the moment about O. Here's an example in 2 dimensions. Here's a force F, resultant F. Say I have forces Fx and Fy. One way is to calculate Fx times d2 plus Fy times d1, and you can see the calculation here, and that will give me a moment. Or I can take the resultant of these two forces and then find the distance from O to the line of action of this force F, and that will give me the moment about O due to this force F. We call this the Vargon's theorem. Here's how to calculate another example. The moment of F about O. So I have a force F applied here with some resultant. I can take that resultant force F and decompose into the X, Y, and Z direction. So what I need to do, the position vector R will have Cartesian components of Xi plus Yj plus Zk. You can see here that I can take the cross product of R and F. The cross product of R and F will now take R cross F will basically be, you can put it here into IJK. You put the R, X, Y, Z, and then you put the force components in the third row. And so then you can now do the cross products very easily, following how to do cross product. For example, if I cross this column and this row, I have I hat times Y times FZ minus Z times FY. And so you can calculate the rest of the components, but this is how you will do it. What about calculating the moment about a point B that's not in the origin? It's the same thing. First, find the coordinates of this point, the coordinates of this point. And so if you have the coordinates of those points, you can now determine the position vector that goes from B to A. And so that's basically subtracting the coordinates in the X, Y, and Z directions of this coordinate and this coordinate. That'll be XA minus XB. That's this component here. YA minus YB. And then ZA minus ZB. That will give you the position vector that goes from B to A. Now, the force components are these ones. And so now all you have to do is calculate the moment by creating this cross product. Here, we will now determine a moment through this example. In this problem, we have to determine the moment of the 90-pound force F, which is acting along the line of action from B to C. It's a 90-pound force, so we know its magnitude, we know its direction because it's telling us is that it's along the line of action from B to C. And then we want to find the moment about point A. So it's not straightforward to use approaches we used in the past. So in this scenario, it makes more sense to then use the cross product of the position vector that goes from A to B with the force vector F. So what is the strategy to solving this problem? First, we have to find R from A to B. That's easy. That position vector is 11 minus 0, I hat, 0 minus 6, J hat, 4 minus 5, K hat. That'll give us the position vector from A to B. Now, how do I find F? this vector F. I know it's 90 pounds, so at least I have that, but I have to find a unit vector now that goes from B to C. And so to do that, same thing, 7 minus 11 I hat, 7 minus 0 J hat, 0 minus 4 K hat, and then normalize it, divide it by the distance from B to C. And that'll give us a unit vector, which when multiplied by 90 will give us the force vector F in the respective components I, J, and K hat. So here you can see the calculation. We've done it for this position vector from B to C. Here's a unit vector. So we follow the same process. Multiply that by 90 gives us the force F along the components, along the directions I, J, and K. And then we calculate R following the same process we talked about, the one that goes from A to B. Now that I have this position vector from A to B, cross product with the force F will then gives us the moment A, and you can see that these are the components of the moment A. Notice that is that has units of force and distance, length, and then it also is a vector as well. So this moment is a vector, and it tells us what that moment is about A. Here's another example. We have two cables, AB and AC, that extend from an attachment point A on the floor. There's attachments at point P and point C. The tension in the cable AB per the problem statement is 10 kilonewtons, and the tension in cable AC is 20 kilonewtons. Is asking us what is the sum of the moments about O due to the forces exerted. And so what we want to do is to determine um, what is the sum of the moments about O due to these forces that are exerted on the attachment point A by the two cables. So we have to express the forces exerted on the attachment A by the two cables in terms of their components. So we know the magnitude. What we need to figure out is how to get the components. And the idea here is to find the unit vector that goes along AC and AB. Once I have that, we can then proceed. So we can do that. The force from A to B can be calculated simply by finding the distance between these 2 points, and then also by subtracting 6 minus 4, 3 minus 0, 0 minus 6. That will give us the components of I, J, and K. You can see that here, the components of I, J, and K. I'm sorry, that one was from BA, not AC, but it's the same process. So 0 minus 4, 4 minus 0, 8 minus 6, that'll give us the components for I, J, and K of that vector. I now take that vector divided by the distance between B and A, and that distance will give us a unit vector there. And so the force AB is 10, the magnitude. So I have to take that magnitude 10 and multiply by the unit vector, and that will give us the components in the X, Y, and Z directions for that force. We can also express the force FAC in the same way. Now that I have the force that points from A to B and A to C, now all I have to do is to determine the vector R. And so I want you to note something, is that I can choose a vector from O to A, right? O to A. That vector is 4I hat plus 6K hat, plus 6K hat. So that's my position vector from O to A. So once I have that position vector, all I have to do now is R cross FAB. R cross FAC and add them up, and that'll give me the total moment, which is a vector. It has units of force and length. So there's two ways of doing it. The lines of actions of forces FAB and FAC intersect A. But another approach that we could have used is as simple as taking the forces FAB and FAC and adding them up first. Once I added those forces, I can then take the cross product of that position vector OA to the resultant force F, since FAB and FAC are concurrent forces. So another approach would have been to add FAB and FAC, add them up, and then take the cross product of R to the summation of these two. And that's a simpler calculation because I don't have to do two determinant calculations like this. Just one is enough to calculate the moment. You get the same answer as you can see here in the bottom compared to the one on the left, on the page before. Example 8 is yet another example in looking at how to calculate the moment. We want to determine the moment about A due to the force exerted by the wire at C. And so I know the tension in the wire is 200 newtons according to the problem statement. So knowing this tension, what is the moment about A due to that force? And so the solution is to find the position vector that goes from A to C, and then calculate this force along the force components along this tension, along this wire. So you can simply determine that by calculating the coordinates of this point A and the coordinates of point C. Once you have the coordinates of point A and C, you can quickly determine the components of that position vector from A to C. And that's simply 0.3 meters I hat plus 0.08 meters J hat. And that's a quick geometry problem. You can figure it out. Next, I will figure out what is the position vector that goes from C to D, but it needs to be a unit vector from C to D. And so what I want to do is calculate the coordinates of this point, the coordinates of this point. Once I have that, I can form a position vector that goes from C to D and divide it by the distance from C to D, that distance. Once I have that unit vector, I can multiply by the magnitude of the tension on that cable, which is 200 newtons. Now that I have that force and its components in IJK from C to D, I can now take the cross product. I can take the cross product R cross F. And so I put the components of that vector here, the components of this vector here, and simply perform the calculation for that moment. There's a slight error here. You can see I have a J hat, and yet I put this number under K hat. So I encourage you to kind of examine the error there, because clearly the position vector AC is in the plane ZX. So therefore, I should not have any components in J hat. It should have been K hat. So that's a mistake here, but it's great that we have a mistake, because you can see how to quickly correct it. Okay, so that's the moment that we find for this problem. Let's now examine the moment of a force about a given axis. There's a lot of situations where this happens. These situations can involve a moment due to a force applied due to a person applying a force along this axis, like a capstan. And these scenarios occur a lot. This force here will cause a moment about this axis here, the vertical axis here. However, if you apply a force downwards, that's not going to cause this axis, this capstan to rotate. You only can apply a force in this direction to cause it on the left hand side to cause it to rotate. Another situation where this could happen is, for example, here's a turbine blade situation. You have a force F that's acting at a particle. This force F will cause a moment about this axis Z. And the question is how to calculate that type of moment when it's about an axis. So to do that, here, one approach is you can take that force F and decompose it into Fz, Fy, and Fx. You can see that Fx passes through the line of through the center line, where about the axis, about where the moment needs to be calculated about this axis. And so therefore, you don't expect this Fx to cause any amount of moment about this. On the other hand, if y does cause a moment about this axis z, and then if z, since it's parallel to the z-axis, which is about the axis I want to calculate moment, this fz will not cause any moment either. Okay, and so what we see here is there is a particular way that we can do this problem. How do we go about calculating um, um, this moment about an axis? So the moment of a force about a given axis. So say I want to calculate the moment of force F applied at a point A about point O. I want to calculate the moment about point O. We already discovered it's R cross F. So it's R cross F. But if I want to calculate what is a moment about axis OL, what I need to do is to project this moment I calculate about O and project it onto the axis along L. And so I need to find the unit vector first, and then I can project M onto this axis. That is the approach to do the problem. It's a very simple process. Calculate R cross F to find the moment about a point along the axis for which you want to calculate the moment about. And then once you have that, you can project that moment, which is a vector, onto a unit vector that's along the axis L, along the line L. And once you do that dot product, you can essentially calculate the magnitude of that moment about that axis. It turns out you can calculate the magnitude of the moment of a force by choosing a position vector from that axis, any point in that axis, to the location where the force is being applied. Doesn't matter where you choose along this line of this line L, at which moment we want to calculate the moment about. And it doesn't matter where you select it, as long as you draw a position vector R from that point to point A and do the cross product of that position vector R to F, you calculate a moment, then take the dot product of that moment with lambda, which is a unit vector along the axis, and it will not matter which point you choose about this line, but you will get the same answer. And so now quickly moving to an example. So let's look at this example where you have a force P, and we want to determine the moment about A. Okay. Then we want to determine the moment about AB, the edge AB, and then about the diagonal AG. So a few different problems here. It shouldn't be very difficult to perform this calculation. The first step to calculate the moment of this force P about A is to calculate the position vector R that goes from A to F. And so you know the coordinates of F, you know the coordinates of A, So it's a simple calculation to determine the components of the position vector R. Once you have this position vector R, and you know the force F, P, and its components, which is given here, you can quickly determine R cross P. And so that's a simple, very simple calculation there. What about the moment of about AB due to this force P? Well, basically what we want to do is take this moment and find the dot product along AB, this vector AB. The unit vector that goes from A to B is I hat, and so therefore I hat dot MA, this vector MA that we calculated will give you the moment about this axis AB. What about a more complicated one? So from A to G, what about this force P? What kind of moment that imparts about AG? That's again very simple. We already calculated a moment about A, so all we have to do is dot product against the unit vector lambda that points from A to G. To find that, we know the coordinates of this point, the coordinates of this point. Therefore, I can calculate position vector, and divided by the distance between these 2 points, I can now calculate the unit vector. So now I basically take MA, which was calculated in the first part of the problem, which was the moment of this force vector P about A. We just take that and apply it against the dot product of lambda. And that's a straightforward calculation, and that's how we calculate the moment about that axis. In example 10, we examine a situation where you have 3 forces applied, and these 3 forces may produce a moment about the x-axis, y-axis, and z-axis. The goal of this problem is to determine the moment caused by these forces for each of these axes. So let's start with the x-axis. For the x-axis, the load F3 is parallel to the x-axis. So that force will not cause a moment about the x-axis. The F2 load, which is 50 pounds, is 2 feet away from the x-axis. That will produce a moment in the positive x direction, and that's going to be 50 pounds times this distance of 2 feet. That's the second term right here. The 60 pounds is 2 feet away from the x-axis, and it can produce a moment about the x-axis, and that's going to be 60 pounds times this distance of 2 feet. So in total, we have 220 pounds times feet for the moment, the total moment caused by these 3 forces about the x-axis. We in the previous examples, we use vector notation to solve the problem. You could do the same thing here. You can use vector notation to solve the problem. Let's look at the forces that will produce a moment about the y-axis. F1, in this case, is parallel to the y-axis, so it's not expected to produce a moment, and that's why the first term here is 0. The force F2 here is going to produce a moment about the y-axis, and so we have to look at the distance from the F2 to the y-axis, the line of action, and we see it's 3 feet away. So 50 pounds times 3 feet produce a value of negative 50 pounds times 3 feet is negative because when you use your hands to determine in which direction the moment is acting, it's actually acting the opposite y direction. Now we look at the F3 load, the 40 pounds. This 40-pound load is how far from the y-axis. It's going to be 2 feet from the y-axis. So again, so 40 times 2 feet, that'll produce a moment about the y-axis. That's minus 130 pounds times feet. I could have used the approach discussed earlier, which is using the vectorial notation, but here it's a simple problem, so you can just do it in a very simple way. About the z-axis, we realize that F2 is parallel to it,
So F2 does not produce a moment. We also know that F1 passes through the z-axis. So this one will not produce any moment about the z-axis, so that's why that's 0 as well. The 40-pound is 2 feet from the z-axis, so therefore we expect it to produce a moment of minus 40 times 2 feet, and that's going to be minus 80 pounds times feet. And note this negative direction because that moment causes a moment that's opposite to the z direction, the positive z direction. So I hope this example um, illustrates how to do it, how to do this problem in a simple way. You could use vectorial notation, but in this case we're not because it's a relatively simple problem. In problem 11, we want to determine the moment MAB produced by the force F. So what is the moment about the AB axis produced by the force F? So what is the strategy? The strategy is to determine the moment either about A or B, doesn't matter. And what you want to do is you want to calculate a position vector R, and the R position vector, you can point it from B to C, but the first step is really to define the unit vector along AB first. So you can, you can do that first. So if you know the coordinates of this point B and the coordinates of this point A, it's relatively simple to find the vector that goes along A and B. And so to do that, the coordinates can be used to determine that the coefficient for I hat is 0.4, the coefficients for J hat is 0.2. I know the distance between A and B, and that's a relatively simple calculation. So now I have a unit vector that defines the direction of the AB axis. And that's as simple as dividing this vector, position vector, divided by the distance between A and B. So that gives me a unit vector. Once I have the unit vector, now I want to find a vector R, which is directed from, it can be directed anywhere from A, B. So I can draw a position vector from A to C, from B to C. It doesn't really matter how you define that, where you pick that point. So the position vector can be defined very quickly. You could define it as simple as RD equals 0.6 I hat. That will be the simplest choice to calculate the position vector to point C. Okay. Um, And so here, RD has been chosen so that it points anywhere in the axis AB to anywhere to the point of action of the force. And so the simplest vector that you can see here is the one that points from A to the line of action of that force. So that's a simple one. That's only this distance here from A to the line of action of this force, and that's 0.6 I hat. So that's a simple way of doing it. The force is F, of minus 300 newtons in the z direction, but negative direction. And so now all I have to do is to take the cross product of R to F, and then once I calculate this, I can calculate the moment about A. And once I get the moment about A, I'm ready now to project that moment on the AB axis. And that's simply by doing the dot product of UB, which is the unit vector that defines A and B axis. And so once I have that cross product completed, RD cross F, that'll give me the moment about A. Then I basically dot product against UB, and that gives me the moment about the AB axis. You could also have selected a different vector like RC. So RC will go from A to C here, find that vector, calculate the cross product, and that will give the moment about A, and then find the dot product of that moment on against this unit vector here. So you'll get the same answer regardless of which method, which vector, position vector you use. Um, so now let's discuss the moment of a couple. In this example, or in this part of the class, what I want to teach you is that if you have two forces F that have the same magnitude and they're parallel to each other, and we call this a couple. They're said to form a couple. And this happens quite a bit in our class. You can determine that the moment of this couple is simply a the force, the magnitude of that force times the distance, and that will give you the moment. This moment, how can I prove that this is the case? So one way is to calculate, say I want to calculate the moment. And so the moment will be R8 cross F about O, for example, R8 cross F, so if I want to find the moment about O, and then RB cross F, so to point B here. So this is position vector there. And so you realize here that because of the negative sign F, that in essence, you have RA minus RB cross F. But it turns out that the difference between these two vectors is really a vector that points from B to A. And so in essence, R cross F will be the moment for this couple. It turns out that the magnitude of R times the magnitude of F sine theta, that this is really R sine theta is the distance between these two forces. So in essence, the moment is just force times d. So I just derived it for you so you can see it for yourself. The moment of the couple is independent of the choice of the origin of the coordinate axis. It is a free vector, so you can apply this moment anywhere you want. It doesn't matter because it will have the same effect. And in general, you can just put that moment anywhere you want. It will not matter. So anytime you have two vectors that are parallel to each other and they have the opposite sign, just put the moment. You can calculate the moment by just simply calculating the force times the distance and putting that moment vector anywhere you want. But it's important to understand that the direction of that moment is going to be perpendicular to the plane that defines F minus F and F. Okay. A couple is a sum moment about produced by two forces of equal magnitude but opposite direction. Here's an example of a wheel. You can apply a force F on the bottom, a force F to the top. And again, it's a moment without net force. So here you can see that this force and this force cancel out. And in essence, there is no net force, but there is a moment caused by them. Typically, there's no effect on moving the object as a translation. The moment, the couple, like I discussed before, is a free vector. The magnitude, so like say I have this example of the two forces. These two forces, when added up, gives you zero net force. And let's say I want to calculate the moment about O. So then I have force times A. So that's this one here. Force times A plus D. I have this one here. And you can see quickly that A and A cancel out. So I get FD. So this is another way of showing you the same result we got earlier in a simpler manner. Note that the magnitude does not depend on the distance between point O and the force F. It only depends on the distance between the two forces. In 2D, you can put a C typically to describe a couple. These are different ways of describing a couple in 2D. A couple is a free vector. To remind you, it can act at any point since M only depends, the moment vector only depends upon the position vector R directed between the forces. And that's the important consideration here. And again, R is pointed from the force vector F to the other force vector F in the opposite direction. And so R cross F will definitely give you the moment, which is a couple and does not depend on the location. You can put it anywhere. Two couples will have equal moments if you have the scenarios of, sorry about that. Two couples will have equal moments if force F1 times distance 1 equals force 2 times distance 2. It's possible that could happen. The two couples lie in parallel planes, and the two couples have the same sense or tendency to cause rotation in the same direction. So you could have two couples that will have equal moments, but they have to be lying in parallel planes, and the couples will have to have the same tendency to cause rotation. So how can you accomplish that? Well, the force F1 must be larger and D1 can be smaller. In this case, F2 could be smaller and D2 could be larger, but the multiplication could be about the equal. And so in that case, you could have two couples with equal moments. You could add couples together. It's not a problem. Say I have a vector F1, force F1, force F1 here, force F2 there, force F2 there. You can see here that F1 and F1, which are opposite in direction, can cause a couple. And the value is F1 times this distance. You also have F2, which is in the opposite direction as this F2, and that also causes a couple. And the point here is that you could add these forces, F1 and F2, and get a resultant R. This resultant R will be the same, but in the opposite direction, and then you can just calculate a single couple that basically calculates R times the distance between the two forces. So that's an important finding from this one. Here's some examples we can go through. Here's an example number 12. Determine the resultant couple of the three couples acting on the plate. So what is going on here? Very simply, what I can do is I can identify all the couples that all the forces that are in the opposite direction and same magnitude. And then I can just basically calculate the moment due to these couples. Note that if there is a couple, that these couples will act anywhere and doesn't matter, I can just add them up. Here I have F1 and F1, and these forces are same magnitude, opposite direction, the distance is 4 feet. So this is 200 times 4 feet, and that's 800 feet. This couple, because this couple is the force is going upwards and this going downwards, it acts in a clockwise direction. So the moment is in a negative direction. So your thumb will go into the page, and that's why you see 200 pounds times 4 feet. Here is the first term, and it's negative. Then I have this couple right here. F2 has the same magnitude as this one here. And so I could take the 450 pounds multiplied by this distance of 3 feet. And that's that one is positive because these forces will cause a counterclockwise moment, couple. And then finally I have this load and this load here. And the distance between them is 5 feet. So 300 pounds times 5 feet is this one here, and that causes a clockwise moment, which is in a negative direction. So I can add them all up, and I get 950 pound-feet as the couple. Here is yet another example, which is example 13. The question is, given this force of 600 Newton and this force of 600 Newton and is directed 30 degrees, to calculate the couple acting on the gear. So I'll we can do several ways. We can calculate the distance between these two forces, or one approach is to decompose this force into the x and y direction, and that's done here. You should be an expert at this point on how to decompose these forces. The one that goes horizontally is 600 times the cosine of 30 degrees. The one that goes downward direction, 600 times sine of 30 degrees. You can see that here. And the force here can also be decomposed very similarly. Now I have two set of forces that are parallel in an opposite direction. You have this force and this force. And I know their distance, that's 0.2. And then I also know this force and the distance. So it should be relatively simple to calculate the moment. And so that should be a very quick answer. That's an easy answer. That's 43.9 Newton times meter. If you did the calculation, that's what you will get. The other approach is to find this distance and then basically just solve the problem. And that's a purely geometric problem that can be easily done. But again, several ways of doing the problem. It just takes a lot more work to find this distance, but it can be done. It's just a geometric problem. In example 14, and notice how we're not, they're very simple problems to do. Here I have to determine the couple moment acting on this pipe. The segment AB is directed at 30 degrees below the XY plane. So this is your XY plane, and this slightly rotated downwards with an angle 30 degrees to this plane. And so I have a force going upwards of 25 pounds. I have a force going downwards of 25 pounds. And the question is, calculate that couple. I can draw a position vector RB and RA. That's one way of doing it. If you do that calculation, you can just add everything up and you get the value of negative 130 J hat. That's one way of doing it. And then what could be another way of doing it? The other way of doing it is to take moments of the coupled forces about a point line on the line of action of one of the forces. So all I have to do is calculate R from this point to that point, and then just simply take the cross product of R against 25. And so when I do that, I get the same answer of 130 minus 130 J hat. So very simple calculations can be performed. You could also use a scalar analysis to determine the answer. If I can figure out the distance between this force and that force, which is this distance d, then I can do the calculation. That's distance d, since this is 6 inches and this is 30 degrees, this d will be 6 cosine 30 degrees. And so once I have that, multiplied by 25 pounds gives me the same answer as the previous approaches. In example 15, the question is determine the components of the single couple equivalent to the couple shown. So here I have a couple, here I have a couple, here I have a couple, sorry, here I have a force, and they're acting in the opposite direction. And then I have a force there and a force there acting in the opposite direction. Again, one approach is to find the distance between the line of action of this force and that force, and this one is easy. I know that the distance between them is 30 times 18. So that'll give me the moment for that one. But this one, I could perform several tricks to solve this problem in a simpler way than rather than finding the distance between this force and that force, which will involve geometry. But it can be done. So what I'm going to do is to take these 20 pounds, okay, and have these 20 pounds. What I'll do is apply 20 pounds in this direction, 20 pounds in this direction, but these 20 pounds cancel each other. So in effect, they're doing nothing. And so what I can do now I have a force here and a force there. That produces a couple. I have a force here and a force here that produces a couple. So that's one way of solving this problem. So this the 30-pound one gives me a 30 times 18. So that's this first one, and that's acting about the x-axis that moment. The next one is I have these 20 pounds and these 20 pounds. So 20 times 20, 20 times this distance between the two forces gives me 240 pound times inch. And that's acting in the positive y direction. And finally, I have these 20 pounds and these 20 pounds, which are at a distance of only 9 inches. And so now I have 180 pounds times inch in the z direction. So that would be a quick way of doing it. In vector notation, it will be m hat, and then you can put these components in each of the I, j, and k directions. So that's one way of doing this problem. Or another approach is to figure out a position vector that basically, you can see here that only these forces here and these forces here produce a moment. So one way is to take the moments about D. And if you take moments about D, what happens is that these forces don't contribute to any moment about D because they go through the line of action of D. And so their line of action goes through D. And so all you're left with is this force and that force, and calculating moments about D should be simple. And here you see the answer for this problem. We can yet have another example here, which is to determine the sum of the moments exerted on the pipe by the two couples. I have this moment here, this force here, opposite direction, same magnitude. I also have this force here, opposite direction. This one is easy. Again, decomposing to the y and z directions to make it easier. And quickly you can see that these two forces are in the opposite direction. These two forces in the opposite direction. And so it's simply taking this force magnitude times their distance of 4 meters, these ones as well times 4 meters, and then this 20 and 20 times 2 meters. And you can quickly put that in vectorial notation and proceed forward. So we will discuss now equivalent systems. You have two sets of systems, system 1 and system 2. And we say that two systems are equivalent if the summation of the forces in this system is equal to the summation forces in this system. And we also call it equivalent, or it needs to be equivalent if also the sum of moments about an arbitrary point P for this system and for these systems, they're the same. So again, if I sum all the moments about a point P for this system and I sum the moments of all the forces and moments I have about a point P here, when I add them up, if this moment is the same as this moment about an arbitrary point P, then we call these two systems equivalent. So it doesn't matter how complicated a system of forces and moments may be, it can be represented by a single force acting at a given point with a single couple. So that's the beauty of this finding, is that system 1 can have a bunch of forces, a bunch of moments, but I can simplify the problem into a single force and a single moment. There must be a way of doing it. And so now we look here at two systems. Here you have parallel forces, and then you have system 2 with a single force. You also have system 1 with concurrent forces, and it can put a single force F. Now you have to find this force F so that the moment produced by system 1 is the same as the moment produced by system 2. Here is an example of a force vector F that I want to calculate the moments about O. So that's R cross F. Um, one approach is to attach equal and opposite forces about a point O, like this, such as this, and the three forces, these three forces may be replaced by an equivalent force vector and couple vector. It will give me a moment about O in this way, and this force F stays there. This moment is basically produced by these two forces in the opposite direction. So that's basically a couple, as an example. So I'm able to find a system here, system 1 and system 2, that basically produce the same answer. Um, and again, two systems of forces are equivalent if I can reduce them to the same force coupled system. Again, I can have a bunch of forces. If I sum moments about O, if the summation of all these forces give me the same resultant of this one, and the summation force says the contributions to the moment about O for this system is the same as this one, I can call system 1 and system 2 equivalent. Let's look at a couple of examples here. Example 17. System 1 consists of the following forces and couples. So I have a force vector FA, a force vector FB, and they're provided here. The vectors are provided to you. There's also a moment of this magnitude and direction here. So suppose I want to represent system 1 by an equivalent system consisting of a force F acting at the point P with these coordinates, and a couple system and a couple M of some kind. So the question here is determine F and M. So how do I do that? What is the strategy? Well, to find the force F is as simple as adding FA plus FB, and that will give me a resultant force, and it will give me the magnitude and direction, or the components as well, for this force. So FA plus FB gives me this, and so basically system 1 and system 2 are so far equivalent. We've made them equivalent. And so now I have to come up with a moment that if I work to some moments about point P, I can then calculate what the moment will be for system 1. So to do that, I have to take the cross product, and so we figure out first to find moments about P, right? We have to find moments about P. So we have to draw a position vector from P to the line of action of FB anywhere, and from P to the line of action of FA. And that's simply, on this case, is just 4, 3, minus 2. That's the position vector. And I know FA is given to me, so I can quickly line them up here in this determinant. And then for from point P to this point here, we know the coordinates of this, the coordinates of that. So that's as simple as 6 minus 4 is 2, 0 minus 3 is minus 3, 0 minus minus 2 is 2, and that's what's lined up here. I know the components of FB is given to me 30I hat plus 5J hat plus 10K hat. So I can line them up here. In addition to that, I have a moment provided to me, which is this one right here. So all three have to be added, and when I add them, I get this moment about P. And so this is how actually you find an equivalent moment at point P. Let's look at yet another example, example 18. The question here is system 1 consists of two forces and a couple acting on a pipe. So I have this force here and this force here at an angle, and I have a couple acting on that pipe. So the question is represent system 1, this system 1, by single force at the origin, such as this one, in a single couple. So what will that be? What force and moment will make system 2 and 1 equivalent? And then the third problem, the second part of the problem is there a single force I can apply that will give me an equivalent behavior for system 3 versus system 1? So to get to part A, which is to figure out what a force F should be, it's as simple as adding all the forces up. And so that's what we've done here. That's simple. And then what I want to do is to find the moment caused by these forces onto O, right? That's what we want to do. And so here, you can see the calculation here very quickly. It's 30 kilonewton times 3 for this load. And then this one has two components, 20I and 20J. 20I, this one has no effect on creating a moment about O, but 20J does. So 20 times the distance of 5 gives me this second value. And then I have this couple of 210 kilonewton. And so I can add them up straight to 400 kilonewton. So these are the force and moment that will represent the system 1 in an equivalent way. For system 3, the sum of forces in systems 2 and 3 are equal. So the forces, the force vector will stay the same. That stays the same for trying to get something like this, system 3. But we need to figure out what distance away I need to apply this force to create the same moment. That's really the question that's being asked. And so for system 3, I know I have 50 kilonewtons. How do I know that? Because I have 20I and 50J for the total force. 20I does no moment about O because it goes through the line of action goes through O. So only 50 does that. So 50 times its distance has to give me 400 kilonewtons. So I can solve for D, and once I do that, I get 8 meters. And so here's another way, another example of how to determine equivalency between various systems. Here's another interesting example. In this example, I have forces applied they're parallel. And the question is, if what force F needs to be applied, and where does it intersect the XZ plane, so system 1 and system 2 could be equivalent. So here we simply add all the forces together for this system. So I get 30 minus 10 plus 20J, and I get 40J. So we know it's 40J, and that's done. Now we have to sum moments about an arbitrary point for this system and make sure they're equal. But we don't know the coordinates of this point, so let's just call it X, Y, and Z. And so for system 1, I put X, Y, Z. System 2, I meant 0, 40, 0 for system 2, because I already found that the total amount is 40. And what we're going to do is sum moments about O, which is relatively simple. And so all I have to do is to determine how much moment each of these forces cause about O. And so that's, again, as simple as drawing a position vector from O to each of these forces. And once I do that, I can calculate the determinant. I know the force orientation. Once I do this calculation, I find that this determinant. You find that the coefficient for I is this much, the coefficient for K is this much. You can now simply solve for Z and X, and it tells you the location where X and Z, where that force needs to be applied to get an equivalent system. That's a great example of the application of this. Here's yet another example, example 20. In this example, you do have a support, but let's ignore it for now. And the question is to compute the resultant for the forces shown and the resultant couple for the moments of the forces about A. And so that's a simple ask. Part B is asking us to find an equivalent force couple system at point B based on the force couple system at point A. Let's tackle part A first. So for part A, again, very simple process. Add all the forces up, and so you get 600 Newton downwards. So now we want to find a moment um, that's equivalent to this system here. So first, I have to calculate the moments about A. And so I have 600 times 1.6, 100 times 2.8, and 250 times 4.8. And that's exactly what you see here. You add them up and you get the moment about A. And this system should be equivalent to this system. If for part B, what I want to do is determine, I know the force needs to be the same, but what moment do I need to apply to get this system to be equivalent to that one? And that's as simple as looking at how I don't know the moment, but I have to make it equal to the system above. So so the force does not change. It's 600 newtons. It stays the same. The question is how we handle that. Well, the moments about B gives me 600 newtons times 4.8. That'll give me 2,880 newton times meter. So I have a moment there. And so now I just have to add this moment to that moment, and then I get 1,000 newton times meter. And so now I have an equivalent system um, and all three systems are equivalent. This one, and then the original problem. And you can verify the answer by taking moments about B. Uh, um, if you do that, then it will be 100 times this distance, 600 times this distance, 150 times this distance. And you'll find the moment about B that'll produce the same equivalent moment system. Example 21 shows three cables which are attached to the bracket. We want to replace the forces with an equivalent force couple system at A. How do we do that? So we want to determine basically find the components of each of these vector along the x, y, and z directions. Once we do that, we can just add all the forces together, and then we can calculate an equivalent moment about A um, for the system. First, we can find the position vector from A to B, A to C, and A to D. The force can be put in the rectangular components very simply for each of the forces, FB, FC, and FD. So these three forces can be put into a rectangular coordinate system. We all know how to do that. If I add all these forces, I get a resultant, and that resultant is this much, and that resultant is acting at this point. Then what is a moment? The moment is basically taking R and crossing against each of the locations where the forces are applied. And the step is really to find those position vectors. These position vectors is the key. Once I know the force components, I can then put in determinant format and do the calculations and add them up. And these moments will be the equivalent moment and force that represents an equivalent system to the original problem. And so what I'm going to do in the next lecture is going to be to do additional examples. So for now, we're going to conclude this particular lecture, and I'll see you next time.